Good morning. We are continuing on with Chapter 30. This should be our last day of looking at Chapter 30. What we have started with now, we're kind of in the last third of the chapter, and the rest of the chapter pretty much is going to be dedicated to looking at circuits that are being driven by AC power sources. So here is our AC power source, we said, and we're starting off with, the real basics here. Here's a power source. It's got a certain voltage, a certain peak voltage, and it's got a certain frequency to it, certain frequency, and there's a resistor in the circuit. So what we're going to eventually get to are resistors, capacitors, and inductors. Right now we're looking at the simplest device, just a resistor in an AC-driven circuit. So the voltage, if I get a voltmeter out and measure the voltage across the resistor, well, it's the same thing as the voltage across the power supply. And what we're going to do with all of these devices, it turns out, for kind of the simplest way to present this, is we're going to start off with the current in the circuit and say, hey, if I've got a power supply that is oscillating at a certain frequency in terms of voltage, then the only possible current that I'm going to end up with is a current that's oscillating with a frequency that matches the frequency of the power supply. It's not like the power supply is at 60 hertz, but the current's going to be at 65 hertz. The current is going to be driven at that same frequency. Now, if we start with the current, and what we've done is we've chosen to represent the oscillating current as a cosine function. So we're going to work from harmonic functions here. Our power supplies are built to give us voltages that are either sine or cosine functions, and we're going to work from cosine omega t for the current. Now the voltage across the resistor is going to be given by R times I, and that says that the voltage across the resistant, the way it's oscillating, is exactly in phase with the voltage across the power supply. So the current and the voltages are going to be in phase with each other. And so I can write both of those as a cosine function. And that's the key feature here, is that they're both representable as the same functions. And then what we had gotten to, where we kind of ended last class, was we started looking at the inductor and said the inductor actually introduces a little complexity to this. And the reason why is the voltage drop across the inductor is not proportional to the current. So it's not the current and the inductor that are in phase with each other. The voltage, the current and the voltage is actually in phase with di dt. So what we have to do is this. We have to take our current function, again the blue line is the current, that's going to be our reference that we're going to work from. If the current is varying like a cosine, then the voltage, which depends on L di dt, is going to be varying like a sine function, specifically a negative sine function. And when I take a derivative of the current with respect to t, it's going to bring out a factor of omega. So here is that factor of omega. I'm going to still have my factor of I naught, and I'm going to have a minus sign out front. So what that says is the voltage is behaving like the sine of omega t. Now if that's the current, I naught, that omega L is behaving like a resistor or a resistance. It will have units of resistance, and what it's saying is that when I put an inductor in a circuit that is being driven by a AC power supply, this is, I think we said this on the last lecture, this is like the inductor's worst nightmare, because inductors like nice steady current, and now what we're doing is we're constantly trying to oscillate the current through the inductor, and the inductor puts up these opposing back EMFs, and that creates something that's equivalent to resistance. So the inductor will have resistance, and if we were to take the frequency of these oscillations, as we turn the frequencies of the oscillations higher and higher, let's say we start oscillating the current faster and faster, how's the inductor going to respond with that? And that's going to put up even more resistance. So what we find is the effective resistance of an inductor in an AC driven circuit is given by omega times L. It depends on how much inductance we have, and it depends on how fast we drive the circuit. On the other hand, if we turn the frequency way down, so let's turn the frequency way down, the inductor doesn't mind that very much, and it's not going to provide as much resistance. So when we graph the voltage is out of phase. Okay, that's a key feature that we want to keep in mind. So again, what we're coming back to is identifying that the voltage across an inductor, they've written this as V naught, but the voltage across an inductor is given by the current times this new quantity, it's the omega times L. It's the same thing we saw on the last slide. But they're giving it a new symbol. They're calling it big X, and it's referred to as reactance. And since it's coming from the inductor, we put a little subscript L on that, and we call it the inductive reactance, and the inductive reactance has units of ohms, and it behaves as a resistance. It behaves the same way that the resistance in a resistor does for an AC circuit. So we want to keep that in mind too. Now I've got an inductor, and it's got kind of these interesting properties where it creates resistance. So let's try this. What we're going to do is we are going to look at a coil, a solenoid, and this solenoid has a resistance. Now, in the slides, the resistance was listed as 1.00 ohms. I don't think that's what they meant. I ran through the numbers on this. So I'm going to change this. I'm going to take this decimal out and say the resistance is 100 ohms. So let's say that we've got a resistor and it's got 100 ohms. And there's an inductor, and the inductor has 0.300 henries or 300 millihenries of inductance. So those are the values for R, and those are the values for L. What it says is, first of all, let's take this solenoid, this coil of wire, and let's hook it up to a 120 volt DC power supply. Now, I don't know of any 120 volt DC power supplies, but I know they're trying to make a comparison between what happens with an AC power supply versus a DC power supply, so they're using the same voltage. That's fine. So first of all, 120 volts DC, and then 120 volts AC with a frequency of 60 hertz. How is the circuit going to respond under those two circumstances? So here we are. Now, I put the AC circuit kind of prominent, I felt like, over on this side, and then the DC is really kind of the reference. Now they ask us to go ahead and just remind ourselves how a DC circuit would work. So let's see. Here is an AC power supply that has a certain voltage. Now they're going to say let's go ahead and work in terms of RMS values. That sounds fine. So the RMS value is 120 volts, and the peak value from the power supply is going to be 120 times the square root of 2, and that gives us 170. So these are kind of typical numbers. They're the frequencies and voltages of our outlets. And then the frequency at 60 hertz, that's the same thing as 377 radians per second. So here's the circuit, AC power supply, here's the resistor, here is the inductance, and since it's an AC driven power circuit, the inductor is going to have an effect. So I've got to consider what effect will the resistance have, what effect will the inductor have. Now, when I hook this up to a DC power supply, I can ignore the inductor. If the current is going to be steady, then d I dt is equal to 0. There will never be any voltage drop across the inductor. So maybe what I should have done was leave the inductor in place and just emphasize there's no effect. There's not going to be any voltage drop across the inductance. That means that the full voltage will be across the resistor. Now what they said was, this is a coil of wire, and we have to ask, well, is a coil of wire, is that a resistor? Or is that an inductor? And a coil of wire is both. So a coil, like a solenoid of wire, it's going to have resistance because it's got, you know, some of these coils of wire in the lab, they've got like a kilometer of wire on them. And it's just wound around. In fact, we have some inductors in there that are coils that have many, many kilometers of wire all wrapped around one pretty compact device. So it's going to have resistance and it's going to have inductance both. So we can write that as if it's got two separate properties built into one device. And over here on the DC side, what we're saying is, since the inductance property is not going to come into play for a DC-driven power supply, I'm just ignoring it. So, chapter 26, voltage is 120 volts, resistance is 100 ohms, it's not 1, it's 100, and that says that the current is 1.20 amps. That sounds perfectly safe. That 1 ohm made me a little nervous. You know, if all I've got is 1 ohm here and I got 120 volts, it's going to give me 120 amps, which sounds like, I don't know, 10 times too much. It's going to throw all my circuit breakers in my house. So again, putting the resistance back up at 100 seemed to work pretty well. And so the current I'm getting is 1.20 amps operating off a DC power supply. All right. What happens with an AC power supply with sort of the same specifications? This time it's an RMS. It's an alternating voltage, but kind of the average value is the 120 volts. So for this, what we have to do is stop and take a look at how much resistance the resistor will produce. So the resistor is going to produce some resistance. Now, in addition to that, the reactance of the inductor is also going to present some resistance. So I've got two different types of resistance. The resistance from my resistor, the resistance from my inductor. They just go by different names. So resistance in the resistor is called resistance. Resistance in the inductor is called inductive reactance. And the combined effect is called impedance. So let's see how we add those together. Now, the resistance we said is 100 ohms, but to calculate the resistive effect of my inductor, its reactance, we need to take omega times L. Now, omega was 377 radians per second, and the inductance is 300 millihenries. Combining those together, what I found was 113 ohms of inductive reactance. So now what you might be thinking is that I just add the two resistances together, maybe it's going to be 213 ohms, but that's not true, and that's because the voltages are not in phase with each other. If I get out a voltmeter and I can't do this because it's built into one device, but if there were some way to take that coil and separate resistance out from the inductance, and then put a voltmeter across the resistor and a voltmeter across the inductor, and then graph those, what I would see is that they're out of phase with each other. And because the voltages are out of phase with each other, the resistances are not going to add together simply through addition. What's going to happen is, because the voltages are out of phase by a half pi, by a fourth cycle, I also have to combine the resistive effects using what's called a phase or an impedance diagram. So for my impedance diagram, what I do is I put resistance from a resistor in the horizontal direction. I put a reactance from the inductor in the vertical direction, and then I use Pythagorean's theorem. So since the voltages are 90 degrees out of phase with each other, I use Pythagorean's theorem. Pythagorean's theorem will reliably tell me what the overall resistance in the circuit is going to be. So what we're going to do is take the 100 and the 113 and square the 100, square the 113, add them together, take a square root, and it says the overall impedance for the circuit is 151 ohms. So there, that's a little different, but what it's doing is, first of all, it's not too difficult, and it's keeping track of all the phase differences that are taking place. Since I have those nice 90-degree phase differences, I don't have to do components necessarily. What I have is distinct components that line right up with the x and y directions in my impedance diagram. And so Z is just the hypotenuse, and that's at 151 ohms. Now Z, if we do think in terms of voltages, what's happening here in terms of phase is that the voltage across the resistor I could represent in this direction. The voltage across the inductor is 90 degrees out of phase. The combined voltage across both devices is at the direction of Z. So Z is in the direction of total voltage, R is in the direction of voltage across the resistor, XL is in the direction of voltage across the inductor. And what we want to come up with is a phase angle, an angle that tells us how far the voltage is out of phase with the current. The current, remember, we're using a cosine function, and the current is in phase with the voltage across the resistor. So this angle right here says the total voltage and the current are out of phase. The current is lagging behind the voltage by 48.5 degrees, and I got that by using, probably the easiest here is a cosine function. I actually have all the components, so I could use, any trig function will do, sine, cosine, tangent, that's the other one. I could use any of those to come up with that phase angle. Okay, now, we've got all of the impedance determined, and now what we do for AC circuits is we take the total voltage, which we were saying was 120 volts, that's an RMS value, and divide that through by the overall resistance. And the overall resistance here is the 151 ohms, and that says in the AC example, I'm only going to get 0.795 amps. And that's an RMS value for the current, and it's less, it's reduced, and it's reduced because in the AC case, the inductor is creating additional impedance effects, additional resistor effects. And that's how it works. DC versus AC. Here, it just comes down to how much resistance. On this side, there's a series of calculations that lead me to an impedance. Here I've got 100 ohms of resistance, but there I've got 151 ohms of impedance. All right, we looked at the resistor, we looked at the inductor, we did an example with resistors and inductors combined. Let's bring in the capacitor. Let's see what the properties of the capacitor are going to be. Now, if I have a power supply that's alternating current, and I got a capacitor, I can actually continually drive current because the capacitor will charge in one direction, but then it will charge the other way, and then it will discharge and charge the other way. So if I drive it with an AC, it's like the circuit never figures out that the capacitor actually has a gap in it. So current goes through the capacitor in this direction, it goes this way, and I never, fully charge the capacitor. And so it works fine. I can have a capacitor in an AC circuit, and the current just keeps oscillating back and forth through the capacitor. Now, it is the case that for a capacitor, the best way not to notice a capacitor is to have a really high frequency. If I have a really high frequency, the capacitor doesn't really have much time to charge. And as a result, the capacitor does not create much, resistance. So what we found so far is, sure, resistors have resistance. We learned that inductors in AC-driven circuits has resistance. Now what we're going to find out is capacitors have resistance too. And a capacitor has more and more resistance as the capacitance gets smaller and smaller. If the capacitance is really small, then the capacitor fills up pretty quickly, and the circuit begins realizing that there's really not an open path here for the current to travel through. So we'll see that more capacitance gives us less resistance. More capacitance, higher frequencies are going to give us less resistance. If we go through, again, I guess we want to go back and do the same thing we did with the inductor. Again, we're going to use the current as operating as a cosine function. Now, this time, when I try to find out what the voltage is, the voltage is going to depend on the charge, not on the current. So if the current is being represented as a cosine, then the voltage through a capacitor is going to be represented as a sine. And so what we have now is the voltage is going to be like a sine function. That says it's going to be out of phase. Now, an interesting feature then is that the voltage here across the capacitor is like a sine function, but the voltage across an inductor behaved like a negative sine function, and that says that those two voltages can actually cancel out. So if I have a circuit, we're not there yet, but we will be soon, where I have a capacitor and an inductor and a resistor, we can put all three in the same circuit. The effects from the capacitor and the inductor are going to be 180 degrees out of phase, and they're going to tend to cancel each other out, which is kind of an interesting effect with AC-driven circuits. Okay, so we got the graph, we've looked at the voltages. Now what we want to do from the voltage calculations or the formulas we've come up with, we want to identify, in addition to inductors having reactance, capacitors also have reactance. It's a type of resistance, and it depends on 1 over omega c. So as we were saying, if the capacitor has lots of capacitance, or if we oscillate the circuit very rapidly, we don't even know the capacitor's there. It's not going to get in the way, it's not going to cause much resistance. But if we go to low oscillation frequency and kind of low capacitance, then then we are entering the possibility of having quite a bit of resistance due to the presence of the capacitor. So that's it. We're going to call that capacitive reactance, and just like the inductive reactance, it has units of ohms. It's a resistance. It's going to have a resistive effect in a circuit. All right, let's try this. Here is our circuit. It's pretty simple. It's got an AC power supply. It's got a capacitor in it. And they are asking how much current are we going to have going through this. So let's take a look at this example and see what we've got. Here it is, AC circuit, capacitor. That's the only thing I have here. I put some signs on the capacitor, just say that at any instant, the capacitor is going to have some amount of charge on it. The capacitance here is listed as 1 microfarad, and the VRMS is still at 120. Now, the frequency is at 60 hertz, that's our standard outlet, and omega is at 377 radians per second. So, a pretty standard set of numbers. Now, don't get too used to those, because from time to time they're going to throw in an AC power supply that has different properties to it. Different voltages, different frequencies. So it's not always going to be 120 volts and 60 hertz. Now, as far as how much resistance is this capacitor providing, we can calculate that. This is the capacitive reactance, X sub C, and it's given by 1 over omega C, and I know the capacitance, I know the frequency in radians per second, and what that's telling me is that the numbers on the capacitor and the frequency are giving me a reactance of 2650 ohms. That's a good amount of resistance. So we have quite a bit of resistance for this capacitor. And then in this case, since this is the only type of resistance I have, the overall impedance, Z, which Z also means we're getting close to the end of the course, right? Once we start using capital Z, that's got to be the last thing we ever define. Probably not, but we are getting close. Z is equal to X sub C. It's equal to the reactance of the capacitor. And so I can just say Z, the overall impedance, is 2,650 ohms. And same as before, I can take the voltage, divide through by the impedance, and that says that at a frequency of 60 hertz, this circuit will have 45.3 milliamps of current. If that's an RMS value, which it is, for the voltage, then the current also will be the RMS value. So that's it. The only device I had was a capacitor. That capacitor is going to have a resistive effect. We call it reactance. And the overall impedance is exclusively due to just the capacitor itself. Now what they say in the problem then is, okay, we'll calculate the current based on 60 hertz. What if we turn up the frequency? Now, I think they went a little too extreme here. They turned the frequency up from 60 hertz to 600,000 hertz? Really? We're going to oscillate the current back and forth 600,000 times a second? That's, I don't know. I don't know if that's an easy thing to do or not in circuits, but that looks like a pretty large frequency to me. It's giving us a radiance frequency of 3.77 million radians per second. That's a lot of frequency. Now, what we said was this. We said, hey, if we oscillate the current back and forth really, really fast, which we are now, it could be that the capacitor never has time to really charge up very much at all. And if that's the case, we won't even notice the capacitor is there. It's going to be a small effect. And so let's see how much that small effect is. Well, we're going to use the same formulas. What we'll do is we'll come back and still use the capacitive reactance. So we can still use the capacitive reactance for this. But this time, because of this really high frequency, the capacitive reactance is going to be a fraction of an ohm. So we went from, 2650 ohms down to 0.265 ohms. Okay, this is going to throw my circuit breakers. I've got 453 amps going through that wire. That does not sound safe. Not if it's standard wiring in a house or something. Anyway, you can see when we go up to high frequency, that had a major effect on the resistive effect of the capacitors, and now we're getting this extraordinary amount of current coming through. Okay, so capacitors, I don't know if you say they like high frequency, I guess. Capacitors do not mind high frequency. They really like high frequency. So if you go with high frequency, it's like the capacitors aren't going to bother you at all. On the other hand, inductors like low frequency. So that turns out to be very useful. What we can do is we can use capacitors to filter out the low frequencies, and we can use inductors to filter out the high frequencies, and we can kind of shift their values back and forth. Again, we can treat them as a tuner, where we're looking for a particular frequency that's kind of a compromise between what the capacitors like and what the inductors like. All right, so that's our capacitor example. And here's a circuit showing kind of the stuff that we were just talking about. Is that we could have some kind of a circuit. So it's kind of a black box that they've given us here. But what they're saying is, okay, I've got a circuit. Signal is being sent to another part of my circuitry. If I put a capacitor in series with what's going on in that other circuit, what it says is that the high frequencies will make their way through this capacitor very easily. If I'm oscillating back and forth a lot, the presence of that capacitor doesn't really block the transmission of the signal very much. But if I go to low frequencies, the low frequencies are just going to build up charge on the capacitors, and then the signal's not going to get through very well. So I have what's considered to block out the low frequencies, and that's a high-pass filter. So I can design a circuit. I've got all these frequencies, this jumble of different frequencies coming out of circuit A, and this blocks out the low frequencies, so only the high frequencies get to the next stage in processing. On the right, what we've done is instead of putting a capacitor directly in the path, we've put it out to the side. So now when all the frequencies come through, well, the really high frequencies, the easy thing for them to do is loop back around to the original circuit. So in this case, the high frequencies, get diverted, and that means that only the low frequencies end up reaching circuit B. So we can set up circuits using capacitors to either favor transmission of high frequency signals or favor transmission of low frequency signals. An important part of circuit designs. Is this it? Is this it? Are we ready? I think we are. What we've got now is we've got an AC power supply. It's got a certain voltage, it's got a certain frequency. They should write that in. So it's got a voltage and a frequency to it. And it has in series a resistor, an inductor, a capacitor. Now, everything's in series. That's not the only type of AC circuit we could design. We could, for example, we could put these all in parallel. If we put them all in parallel, there are kind of standard ways to analyze that also. We have kind of limited time in the course, so I think we're probably just going to look at the series circuits. I'm not really planning on adding a section on parallel, but we'll see what happens with that. All right, I got a resistor, an inductor, and a capacitor, and what it's pointing out here is that if I bring out a voltmeter now, if I get the voltmeter to measure the voltage across the resistance, it's oscillating. I get a voltmeter out, measure the voltage across the inductor. Now that's oscillating too. Its oscillations are out of phase with the resistor. So they're not in phase with each other. And so we'll see what we have to do in analyzing. And then I got a third component, a capacitor. If I get my voltmeter out and measure the voltage across the capacitor, that is going to be out of phase with the other. They're all three going to be out of phase with each other. Now, what we had said earlier is that the voltage across the inductor and the voltage across the capacitor are 180 degrees out of phase with each other. And that means that they're always going to have opposite orientations with their voltage, exactly opposite, and that means they can cancel each other out. So there's a possibility, if I put, well, this is going to happen. If I put a voltmeter between here and here, it will read the difference between those other two voltages. It won't read the sum, it'll read the difference. And that's because they're 180 degrees out of phase. If I put a voltmeter here and I have 80 volts across the inductor, and I put a voltmeter here and I have 50 volts across the capacitor, 80 and 50 volts, when I put my voltmeter across both of them, I'll get 80 minus 50, there'll be a net of 30 volts across. There's also the possibility, depending on how we've designed the circuit and what frequencies we're operating at, I could get the voltage on the inductor and the capacitor to exactly cancel out. What if I set up the inductor and the capacitor and the frequencies so that this is 80 volts and this is 80 volts? Then when I put my voltmeter across both of them, it's going to read 0. So these phase differences, which we kind of made a big deal about when we were introducing these, the phase difference effects are really showing up. So, which makes the AC circuits interesting and hopefully not too difficult to go in and analyze. All right, so here is a phase diagram. So what we're going to do is we're going to look at what are called phasors. Now, I always feel like the phasors are done more complicated than they really need to be. So I'm going to try and point to things that are useful. And then we'll probably talk more about phasors, but I'll probably identify at least part of the discussion as that's not really needed, at least in problem solving. It's good to know, not really needed to solve the problems. So what we've got right now is this. If you remember, the current had been defined as a cosine function, a cosine of omega t. So on my phasor diagram, what we do is we represent a current as a vector with either its peak or its RMS value, either one. And then we imagine that phasor making circles at a frequency of omega. So whatever the frequency is that we've identified for the circuit, that's the frequency at which I'm going to imagine that blue phasor going around in circles. Now, when this is going around in circles, its projection onto the horizontal x-axis is going to be varying like a cosine. And that's why on a phasor diagram, the horizontal axis at t equals 0 represents a cosine function. A cosine function behaves as if it's the x projection of, again, that blue phasor going around in a circle. If I project down, but when the phasor gets to here, that's at 90 degrees, and its projection back down onto the x-axis is 0. At the end of half a cycle, the phasor is over here, And that says that the current is in the negative direction at peak. And then when it comes to here, it's back to 0, and then it's back to peak value in the positive direction. So that's the direction that the current is in. Now the I naught, again, represents a fixed value, just a magnitude. And again, we think of the whole diagram as rotating. Now, what we found with a resistor is that the voltage across the resistor is directly in phase with the current. So the red horizontal phasor is representing the property of voltage across the resistor. The length of it represents some number of volts. In the vertical direction, this is the voltage across the inductor, and the amount of that is I naught times XL, the same way this was I naught times R. And this has been shifted 90 degrees to take into account the fact that the voltage across the inductor is out ahead of the current by 90 degrees. So we've shifted that relative to the current by 90 degrees and placed it here. So the horizontal line, the voltage across the resistor, that's like a cosine function. The vertical line is like a negative sine function, and the line in this direction, that's the capacitor, that is a sine function. So now you might say, why is that the sine function? Well, because again, if I rotate that capacitor voltage phasor, it initially goes positive. If I look at the projection onto the x-axis, it's in the positive, it starts at 0, and then it starts going positive, and then the phasor goes by, and then it oscillates. This one, if I start here and begin to rotate the picture, this one initially goes negative. And so that is representing a sine function, the arrow down. The arrow up is representing a negative sine function, and the horizontal line is representing a cosine function. Now, to add all of the voltages together, we add these three together, the same way we would add vectors using Pythagorean's theorem. So you can see from this diagram, the voltage across the inductor and the voltage across the capacitor oppose each other, and so the net voltage across both is the difference between the two. The voltage across the resistor is at a right angle, and so that has to be added using Pythagorean's theorem. But at the end of adding all these together, I'll have the overall voltage across all three of the components. So now this is the voltage diagram, and the book has plenty of these, and they talk about it and they discuss it. What the textbook doesn't do, and I think is actually the simplest way to look at these problems, is let's take a look at these vectors. If I take each of these quantities, this is I naught times XL, this is I naught times R, this is I naught times XC. You know what we could cancel out on each one of those? We could cancel out the I naughts. So that would give us a diagram that looks exactly the same, all those red phasors, but the diagram now would be reading XL, R, and XC. And that's what I call the impedance diagram, and I think that's the easiest diagram to work from. We already used it in one of our examples, and I'm going to keep using it. Somehow textbooks are kind of nervous about doing that. I guess there's a feeling that these are fixed values, they're not oscillating, they shouldn't be represented with phasors, but God, it makes the problems easier to do. So we'll keep all of that in mind. I hope at least part of that made sense. Here we go. As time goes on, what we imagine is that the phasors begin to rotate, and the angle that they rotate to is given by omega times t. And again, the individual currents and voltages are the projections down to the x-axis. So at this instant in time, the current is this much. The voltage across the resistor is that much. The voltage across the inductor is this much, and it's in the negative direction. And the voltage across the capacitor is that much. Okay, so think of trigonometry and all of those exercises taking a bunch of different functions with sines and cosines in them and trying to add them all together. That's what this is doing. It's taking a function that's a cosine and a function that's a negative sign and a function that's a positive sign, and it's adding the effects all together. And you can do it all on this diagram. So it can be quite a simplification. There it is. So here, very same diagram, and what they've done is I've identified right at this instant voltage across the resistor, voltage across the capacitor, voltage across the inductor, which is opposite to the capacitor and resistance at this instant. And then the current is right there. Okay, what that says then is if we think of that impedance diagram that I kind of outlined, the overall resistance in the circuit then is going to be given by, first of all, let's start over here. In the vertical direction, I have the possibility of cancellation. If I represent XL vertically upwards and XC vertically downwards, I can cancel those two numbers, and we do that by taking a minus sign. Then I'm going to square that value, and then using Pythagorean's theorem, I'll square the R, take a square root, and get the overall impedance. That's how we get the overall impedance in an AC series with resistance, capacitance, and inductance in the circuit. Now, another way we could write this, the XL, remember, was given by omega L, and the XC, the reactances, were given by 1 over omega C. So omega L minus omega C gives me the net effect of the capacitor and the inductor combined. Now the phase angle, we also looked at this in an earlier problem. The phase angle is going to come from, you can do it in terms of voltages, but I think it's going to be easier, again, using the impedance diagram is the easier way. I can take the net impedance between the inductor and the capacitor. That gives me the vertical component. R is the horizontal component, and then I can do an inverse tangent. Now what you do have to be careful with is you've got to keep the signs straight on the angles. So, you know, the phase angle could be anywhere between plus 90 and minus 90. And depending on how you enter numbers into, the sign should take care of itself, I guess. But be careful. If I'm in the quadrant 1, then the angle is defined to be positive. If I'm in quadrant 4, is that what it is? If I'm in the lower quadrant, the sign's defined to be negative. So make sure you keep signs straight, and we can also calculate phase angles. We did all this in that earlier circuit. It just didn't have a capacitor in it yet. The only thing we really need to add in is something with a capacitor, so let's do that. Here is an example. We're driving an AC circuit using an AC power supply. We have resistance of 25 ohms. We have inductance of 30 millihenries. We have capacitance of 12 microfarads. So this is what these problems sound like. They're all connected in series. That's the only type of circuit we've really analyzed. And it's at 90 volts, 500 hertz. All right, here's one of those unusual kind of AC generators. This is not plugging into an outlet anymore. This is operating at 500 hertz and 90 volts. Find the current. Find out what all of the individual voltmeter readings are going to be. Find the phase angle and find the rate at which energy is being dissipated in the circuit. So here we are. What we have is, here is the RL, there it is. Oh, I didn't write the L, that's the problem. There's a resistance, there's a capacitance, and there's an inductance, there's an implied L right there. They're telling that the overall voltage is 90 volts. Now the individual pieces of the voltage are going to be R times I, XC times I, and XL times I. And what I did up here was I drew phase diagrams. I drew a phase diagram for voltage, but I also drew an impedance diagram. Again, that's my favorite in these problems. That's almost always the first place to start from. So, yeah, let's start from this and see what we have going on. First thing I can see in the problem is, well, they gave me the values for R, L, and C, and what they want me to do, what I need to do, is determine what's the total impedance of the whole setup. How much impedance do I have in this? So, well, the resistance is already taken care of, that's 25 ohms. But to get the reactances, I have to take omega times L. Now, those numbers were given. At 500 hertz, the omega, the radiance frequency, is 3,141. That gave me 94 ohms of reactance in the inductor and 31.8 ohms of reactance in the capacitor. Now, I don't always do this carefully, but if you do this carefully, it probably helps. What I'm doing is taking those three numbers, 25, 94, 32, and I'm drawing my phase diagram, my impedance diagram, to try and match that. So I'm going to try and match, I don't know how, I didn't do very well. Let's see, if this is 94, ooh, that should be like 4 times as big as this. This resistance needs to be smaller. Sorry about that. The capacitor, the capacitive reactance, that needs to be about 1/3. Again, not the best, but it's okay. I did clearly show that XL is a lot bigger than XC, and that means when I take XL and I subtract off XC, I'm going to have this much left over. And that becomes the net reactance. So I'm going to take the net reactance, which is the difference between those two phasors, and combine that using Pythagorean's theorem with the resistance, and that's going to provide the overall impedance for the circuit. So it's looking pretty good. We can combine all those together according to our impedance formula for everything in series. And when I combine them all, I get 67.2 ohms. And by using one of the trig identities, or one of the trig functions, I end up with an angle of 68 degrees. So yeah, that angle, that phase angle phi, should have been more like 68 degrees. It looks more like 40. So not entirely to scale, but pretty useful. Now, we've established that the Z is shifted into the first quadrant, and that's because XL is bigger than XC. So the phase angle is going to be positive. All right, that all looks good. We were able to figure out how much overall impedance we have. But wait a minute, isn't there a problem here? Because the overall impedance is 67 ohms, but look, the inductor all by itself has a reactance of 94 ohms. Is that possible? And it is. So it's one of those cancellation effects that we talked about. So what happens is, because the voltages across the capacitor and the inductor cancel each other out, their resistances also cancel each other out. And that says that what I'm really comparing with is not these individually, but the difference between them. Now the difference between these is like 62, 63 ohms, and 62 or 63 ohms is perfectly fine. So like 60 ohms or something is below the 67, not a problem. This is going to work just fine. Now, moving over to the voltage diagram, we can calculate all the voltages by using ratios. What we can say is, if I look between the two diagrams, voltage C is to XC, as voltage L is to XL, as voltage R is to R, as the overall voltage is to the total impedance. So for each of the individual voltages, I can go through, for the resistor, for example, I can take the resistance with respect to the overall impedance, multiply that by the voltage, and that says the resistor will have 33.5 volts across it from a total of 90 volts. Now, the inductor is actually going to have 126 volts across it. So I'm going to have a section of my circuit. If I get my voltmeter out, my voltmeter, I put it exclusively along the inductor, that's going to read 126 volts. If I now put the voltmeter across the capacitor, what my calculations are showing is that's going to read 42, 43 volts. If I put my voltmeter across both, it's going to read the difference. So it's going to read something like 83, 84 volts if I put my voltmeter here. If I put my voltmeter across the resistor, that's going to read 33.5. If I put my voltmeter across all three, well, that's the same thing as putting the voltmeter across the power supply, and that's going to read 90. So I got all the voltages, I've got all of the resistances, the reactances, oh, we never got the current. That's the most important item. So the current is given by V divided by Z, and it says that I will have an RMS current of 1.34 amps. Now, reading through this again, I missed one of these. Part D says, what's the power dissipated in the circuit? So let's take a look at that and see if there's a way we could backtrack a bit and see if we could add that in. All right, first of all, where's the energy coming from? And the energy is coming from the power supply. So there is a net flow of energy out of the power supply. Where is all that energy being utilized? The capacitor and the inductor take turns storing energy, but then they release it back into the circuit. So there's no net energy loss from the capacitor. There is no net energy loss from the inductor. What about the resistor? Of course, the resistor is going to have a net energy loss. So to calculate the rate at which energy is being lost in the resistor, what we can do is take the voltage across the resistor, the current across the resistor, which is the same as everybody's current. So for the resistor, since the voltage and the current are in phase with each other, I can take the RMS voltage, the RMS current, multiply those together. It looks like it's going to be about 40 watts, maybe in the low 40s. So again, there's a complicated path of energy in and out of the capacitor, in and out of the inductor, but the resistor just steadily loses energy. There's no point where the resistor is putting energy back into the circuit. As soon as you hand energy to the resistor, it's gone. And the power supply is compensating for that. So the power supply just has to supply enough energy to compensate for whatever the resistor is losing. Good example here too. That's a good one to look at, understand all of the details there. All right, let's see. We said this. This is such an important formula right here that in our LRC AC-driven circuit, where the inductor, the capacitor, the resistor, they're all in series, we said that the current is going to be given by V RMS over Z, and the Z, that's what I'm actually referring to here. In a series circuit of a resistor, inductor, and capacitor, the overall impedance is given by that stuff in the denominator. And it can be easily determined, I'm going to claim, using an impedance diagram that we looked at in the previous example. So I'm going to say, use these, really handy. You can use a diagram like this, run the numbers, and then put in the final Z, and figure out how much current we're going to have in that circuit. Now, what they're pointing out here is that not only does Z depend on R and L and C, Z also depends on frequency. So depending on what frequency we operate a circuit at, we're going to have more or less current. We could actually, for example, if we were to take the circuit that we just looked at. So let's take this circuit, we just looked at it. How could I adjust the frequency of this circuit so that the current goes up? I want to get as much current as possible. I'm stuck with the resistor and the capacitor and the inductor that I have, but my power supply allows me to change the frequency. Is there a way, adjusting frequency alone, that I could maximize the current and determine what that value would be? There must be a way to do that, otherwise we wouldn't have introduced it. So here's how we do it. Very same circuit, 25 ohms of resistance, 12 microfarads of capacitance, 30 millihenries of inductance. That's what the circuit looks like. And what we're going to do is this. We're going to go to the right side first. To get the overall Z to be as small as possible, I want the reactance of the inductor to exactly cancel out the reactance of the capacitor. That's doable because I can take omega L, set that equal to 1 over omega C, and then I can solve for omega. And what I found was at an omega of 1,667 radians per second, the two effects, the effect of the capacitor and the inductor, will exactly cancel out. And I can just ignore their effects in the circuit. Seems kind of crazy, but that's what happens because of the 180-degree phase difference between the capacitor and the inductor's voltage. Well, this radiance frequency becomes 265 hertz. So I'm going to adjust my power supply, and instead of operating at, what was the frequency in the last one? Like 500 hertz or something? I'm going to bring that down. I'm going to bring the frequency down to 265, and then I'm going to go back and double check my reactances. So at this new frequency of 265 hertz, putting those values in, actually I'm putting in the 1,667, times the inductance, it gives me 50 ohms. When I check the capacitor's reactance, 1 over omega C, that's also 50 ohms. So when I draw my diagram now, the 50 ohms from the inductor and the 50 ohms from the capacitor will cancel out. We'll cancel out those effects exactly. So all we're left with, the Z value now is exclusively equal to R. It's not that the inductor and the capacitor aren't there, it's that their effects have canceled out within the circuit. So I only have 25 ohms of resistance. Now that's the best I can do. There's no way I can get the resistance or the impedance to go lower than 25. I'm kind of stuck with the resistor. That's going to have 25 ohms of resistance no matter what. But I can now use that 25 ohms, and now I've got the current all the way up to 3.60 amps. What was the current before? Current we had before was 1.34, and at this different frequency we're getting 3.60. Now this effect is called resonance, and it says that this circuit is being operated at resonance frequency. So for any RLC circuit, there's going to be some frequency at which the effect of the capacitor and the inductor cancel each other out. And that's going to be our resonant frequency for the circuit. And it looks like we successfully identified what the resonant frequency would be here. Under those circumstances, the entire impedance reduces down to just the resistor. Now this is a graph. It's showing what happens when you vary the frequency. So if you notice here, this is IRMS on this vertical axis. And what we're doing is we're varying the frequency back and forth. And what it says is, especially in the case where the R is relatively small, if the R is not making much of a contribution to the impedance, then when we cancel out XL and XC, the impedance comes way down. And in that case, we'll have a sharp peak in the frequency range close to resonance. So the resonance frequency here is omega naught, is what they're calling it. 1 over LC square root tells us what the omega naught will be. Now if you get to larger values of R, if the resistance in the resistor is comparable to the impedance that we already had, then it's not going to be such a dramatic effect. But still, we're going to have the current maximize whenever we adjust the frequency so that it's resonance. Now remember, that means you got to have a way to adjust the frequency, right? If, for example, let's say we have a radio tuner and we're getting all of these signals coming in, we're generating currents that represent the signals, and the current is a jumble of different frequencies, depending on how we've tuned the L and the C. So if we go back and make the capacitance or the inductance variable, then we can adjust so that we get the sharp peak occurring for a particular frequency. That lets us tune in to a particular frequency, to a particular signal that we want to listen to. All right, here is a summary of this chapter. There's been a lot, so let's go back and think. This chapter, actually, yes, this very chapter started off with mutual inductance and self-inductance, and yeah, that seems like it was a long time ago. But remember, we made use of Faraday's law, stuff that we had learned in chapter 29. We utilized that and showed what mutual inductance and self-inductance is going to depend on. We also looked at inside an inductor, how much energy do we have? In particular, what's the energy density due to a magnetic field? Now, this formula is not written in terms of little k, it's written in terms of mu naught. Remember, mu naught is 4 pi k over c squared, if you want to convert that back into the version that I'm using in my contributions to this presentation. All right, now we looked at a bunch of different circuits. So first of all, we looked at an LR circuit with a battery in place, and we said that the presence of an inductor slows the increase in current so that it asymptotically approaches some peak value. The current doesn't jump suddenly, it takes some time for the current to build up. And then we're moving down into AC circuits, where we defined inductive reactance and capacitive reactances for circuits. And maybe finally, this might be the end here, this was the overall impedance in an AC circuit, and this is the resonance frequency for a particular value of L and C. So again, if I have a circuit with a variable capacitor, a device where you can go in and vary the capacitance, or a variable inductor, a device where you can go in and vary the inductance, then we can tune a circuit so that it will favor signals that have a particular frequency to them. We can select out a particular frequency that we want to enhance or emphasize in our circuit. And that is it. So any questions? That wraps up chapter 30 for us. So we still have one more chapter. We have chapter 31. Chapter 31 is going to give us a transition kind of out of circuitry. So chapter 31, we're not going to be looking at any more circuits. We are going to use velocity and acceleration fields. In fact, chapter 31 is mostly looking at acceleration fields and how those are used to radiate energy away from sources. So kind of a new topic, should be good.